Um, can you see my screen now, actually?
Yeah.
Okay, cool. All right. So I want you to know some, for example, what kind of pure math have you learned? Okay. So did you learn vectors before? Vector, not factor. Okay. VECTOR.
Yeah. No.
No. Yes or no? Sorry.
No.
No, you haven't learned a vector. Okay. All right. So if no, then we need to start with some probably pure math knowledge first. Okay, before going into the mechanics of vectors. Okay. All right. So first of all, we need to learn what a vector is. Okay. Okay. So intuitively, a vector is like an arrow. Okay. So it's basically a quantity which is indicated by its direction and its length. Okay. So for example, what kind of quantity can be described by such a vector? Okay. For example, when you're talking about an object which is lying on a two-dimensional plane. Okay. And then, for example, you want to talk about the velocity of that vector, of that particle, sorry. Then you probably need to use vector to describe it, right? Because for example, for velocity, you can't just tell us about what is your speed, right? If you just tell me the speed, you can't really understand the direction you are going to. Okay, for example, you can go into the north in 2 meters per second, or you can go into the south in 2 meters per second, right? So that's why we are going to introduce vector in describing the mechanics of objects. Is it okay for the motivation?
Yeah.
All right. So now once you understand this, so here is the more formal definition of a vector. Okay, a vector is a quantity which has both magnitude and direction. Okay, so magnitude means the length. Okay, and direction. So I think you understand what direction means, right? Okay. So is this okay? Is this okay
Yeah.
for, about the definition of vector? Okay, cool. So so next, let's look at some examples of vector. Okay. So for example, just now I've mentioned velocity. Okay, the velocity of an object is a kind of vector. For example, how can you describe it? For example, you're moving due north at 20 meters per second. Okay. So can you tell me what's the magnitude and direction of this vector? What's the magnitude?
20 meters per second.
Yes, exactly. That's 20 meters per second is the magnitude, and then the direction is going to the north. Okay. So velocity is a kind of vector. Okay. All right. Next one is about, for example, force. Okay. Okay. For example, you're to describe force, you need to consider, for example, a force that is pulling in this different directions. Because if your force is pulling from different directions, your the motion of particle could be different, right? For example, if you're pulling an object to the north, probably it's going to the north. and if you're pulling your object to the south, it's probably going to the south. So for a force can be described by a vector, and also, for example, displacement, right? Now, displacement can also be a vector. For example, if you're starting from this position A, and then you're going to the position B, okay, and then you're going to an arbitrary path like this, okay. But anyway, the displacement, remember, that's the distance between the two the initial position and the final position. So the displacement can be described by this vector pointing from A to B. Okay. Is it okay for this?
Yeah.
All right. Okay. So so for example, let's look at the example. Okay. So here we have this a girl walks 2 km due east, okay, from O to A, okay, and then 3 km due south to from A to B, okay. So 3 points here, and then what we're going to do is describe the displacement, okay. So to describe displacement again, we need to describe two things, namely distance between the 2 points and the and also the direction. Okay, so so for this case, we can, what kind of things can we use to describe the direction? Okay, so for example, if you're talking about the 4 directions, namely the east, south, west, and north, you should immediately think of, for example, the compass bearing or the hole bearing, right? These two can be used to describe the direction of an object. So we can describe the direction using.
I have a question.
Yes.
Do they just want the wait? What is what like? How would you answer this question? What's
So
by describing? Do you like find the actual displacement?
yeah. So I would try to remember displacement is a vector. So we need to determine two things, namely the direction and the magnitude. Okay. So we need to find these two things. Okay.
So you just at the end is a triangle, right?
Yeah. So
And you use Pythagoras, find it.
yeah. So you use Pythagoras. So magnitude and direction, these two things. So so if you draw the picture, it will be like this, I think. O to A. This is 2 km. And then you go down, that's 3 km. This is B. And then the line joining O and B will be like this, okay? So so first of all, let's find the magnitude of the displacement, which is exactly just the length of this line OB. Okay, so it's easy, right? You just use Pythagoras. So OB equals to the square root of 2 square plus 3 square, which is exactly square root 13. Okay, so this one is the magnitude of the displacement. Is it okay?
Yeah.
All right. And then next, we are going to find the bearing. Okay. So you have the point B here, right? Then remember, the bearing is counting, for example, the whole bearing. Okay. The whole bearing is counting from the north to this line. Okay. That's the angle between the north direction and this line. So you need to determine this angle. Okay. And then, but you know that this angle actually consists of two angles, namely this right angle 90 degrees, and also the angle here. Okay. So two angles here. Then, then to find the red angle, you only need to find the purple angle right here. Okay. So let's call this theta just for convenience. Okay. Then you know from trigonometry, you know this is tangent theta equal to 3/2, right?
Yeah.
Okay, then you can use the calculator and then take the arctangent at both sides. You get theta is 56.3. Okay, so once you have this, then remember what we want is the red angle. So the bearing is 56.3 plus 90 degrees, which is around 146 degrees. Okay, is this okay?
Yeah.
All right, cool. So so this is the first example that we encounter a vector, which is a displacement. Okay. All right. Next one. Um, now for numbers, we know we have addition, right? We have addition, we have multiplication, etc. Okay. So, well, our question here is whether we have addition or multiplication in vectors. Okay. And if so, how can we do that? Okay. So it turns out that now the first question we will ask is when are two vectors equal? Okay. So equality of vectors. Okay. So we will say two vectors are equal if and only if they have the same magnitude and the direction. Okay. Direction and magnitude. Okay. So that's very reasonable, right? Because as I mentioned, a vector is described by its direction and magnitude. So once they have the same direction and same magnitude, they should be the same vector. Okay. So for example, if we have a vector v, which is like this, and let's try to translate this vector. Okay. So it moves to here, and then this w, this is denoted by w. Okay. And then our question here is, are these two vectors equal according to the definition? What do you think?
Yeah. Yeah.
Yes, they are equal. So v equal to w because they have the same direction and magnitude. And actually that is very important. Okay. Why very important? Well, because we can for example, you have a parallelogram here. Okay. So for parallelogram, you know, the opposite sides, they are parallel, right? They're parallel. So, and then also they have the same length. Okay. What does it mean? Okay. So for example, if I describe this, for example, we have this side here, okay, which is described by vector A. And then also we have another vector which describes this side, okay. Well, do they have the same magnitude?
Yeah.
Yeah, right? Because they are the opposite sides of a parallelogram. And then are they pointing in the same direction?
Yeah.
Yes, exactly. So So, and this is a very interesting example. So that means if two sides of the vector of, two sides of a parallelogram are described by by two vectors, these two vectors are actually equal. Okay, is it okay here?
Yeah.
All right, and then so another operation is about the parallelism. Okay, parallelism. Okay, so we say two vectors are parallel if and only if they have the same direction. Okay, so that's very natural again, right? Okay, so it's nothing special here. Let's get straight to the third property, which is echoing what I mentioned just now, right? We want to define some operations of vectors. For example, we want to define addition of vectors. Okay, so um, for vectors, the addition law has a special name. Okay, we call the law of addition the triangle law of addition. Okay. Okay, so what does the triangle law of addition state? Okay, so for example, you have two vectors. Okay, okay, so for example, this is called the tail. This is called the tip, right? Okay, so in this situation, the tip of this vector is pointing at the tail of the another vector. Okay. So in case the two vectors are oriented in this way, then it's easy to add them. Okay. So if this is A, this is B, then A plus B is essentially this vector. And that's why I would describe this as the triangle law of addition. Because if you have two vectors, when you add them up, then the sum would form a triangle with the original two vectors. Okay. Do you understand this?
Yeah. Yeah.
Okay. So, do you understand why we define the addition like this? Actually,
No.
no. Okay. Actually, it's easy to understand. Well, if you think about A and B as displacement, okay, then you immediately see why, right? For example, you have a particle that goes from along the vector A and then it goes along the vector B. Then A plus B is essentially the overall displacement of your motion, right?
Yeah.
So yeah, so that's the motivation of defining the law of addition like this, okay? So the motivation, let me just put it very simple. Displacement is coming from the displacement, okay? So it's like addition of these two paths, okay? It's the overall displacement. Okay. All right. Is it okay so far?
Yeah.
All right. Next one. Um, some notation. Okay. Now sometimes we want, for example, we are just given 2 points, and then we want to describe the vectors that point from certain point to another point. Okay. So, for example, if you always do it like these things, that's it's very. I mean, it's very complicated or it's very messy in notation because every time you need to define new vector. Okay, so we want to introduce a notation which basically denotes the the vector pointing from a point to another point. Okay, so for example, we have a point A here, we have another point B here. Okay, and then we have a vector pointing from A to B. Okay, and then this vector here, we call this vector AB. Okay, and if you write it by hand, you need to add an arrow above. Okay, now some people now this is my habit. I tend to write the arrow sign as like this, but for some people they write it like this. Okay, this is just the same thing. It depends on your habit. I think this why I keep on using this is because this is more convenient. I don't need to take my hand away from the paper to draw this arrow. That's why I stick to this one. Okay.
Yeah.
All right. So that's the vector AB. All right. And then let's look at the following example. Okay. So let's say we have a parallelogram. Okay. And then let's say we have let me just call this A. Okay. So this is A, B, C, D. This vector is called A, and then this vector is called B. Okay. And what we're going to do is find the vector, find this vector. Okay. All right. So how can we find this vector? I mean in terms of A and B.
It's just A plus B, right? Because
A plus B. Why? Why do you think so?
the AB is equal to CD and AD is equal to BC.
Yeah, okay. Actually, you don't need to move both vectors. You can just move the vector A right to here, right?
Yeah.
And then you see that's the tip and tail thing right here, right? So that's why AC, the vector AC, AC. Vector AC is just A plus B, okay? So you need to master in translating the vectors. That's the thing that makes vector very convenient in doing operations, okay? Is it okay for this example?
Yeah.
All right. Let's find one more vector, okay? This time is the vector BD, okay? What do you think this time? BD.
It's the same.
Is the same? Not really, not really. Because now, first of all, by inspection, they cannot be possibly equal because they're not pointing in the same direction, right?
And it's B. Okay, then
Now for this example, we need to solve for BD, okay? Because A and B now they are not in the tip and tail situation, okay? Yeah, actually there are several ways to do it. Now the first way is first of all we can let's call B the vector BD. If we add A with BD, we will get the vector B. Is it correct?
yeah.
Yeah, exactly. So BD plus A equal to B. So BD is actually B minus A. Okay? Is it
Does
okay?
that work? Wait, I'm confused. In the triangle, the addition law.
Yeah.
Is it? There's like any two add together equals the third?
You mean this one adding this one is equal to this vector? That's the triangle law.
Yeah, but so any two sides
They have to be in the tip and tail orientations. If they are in, they're like
okay.
this, that's the tail to tail. Then you can't add them directly. Okay.
So just now it was tip to tail.
Just now what?
Just now was tip to tail for AC.
Hmm. Yeah. If I translate this A to here, they are in
Yeah.
to tail. And then if you add them, you get the vector AC here.
Okay.
But
Okay.
yeah,
Okay. I see. I see. I see. Yeah. Okay.
all right. That's the first way we can do we can find the BD. And also, actually, we can do it in another way, okay? And then we can make sense of what does it mean by negative over vector, okay? So alternative way, so now this time you see for the vector A here, again, as I mentioned, they are not in the tip to tail situation, right? But then, well, if you think about this, okay, if we reverse the direction of A, then the new vector will be in the tip and tail situation with B, right?
Yeah.
Reverse the direction of A. So here let's maybe define what negative A means. Okay, negative A should be the vector uh, pointing in opposite direction of A. Of A, and then also and has the same and having the same magnitude. Okay, that's our definition here. Okay, can you understand this?
Yeah.
Yeah, so that's how we define negative a vector. And then in this case, then obviously BD is just negative A plus B, right? Yeah, then BD equals negative A plus B, which has the same result as above, right? We get B minus A here, and the bottom here is negative A plus B, which are the same thing. Okay.
Yep.
All right. Cool. So this is the way we add vectors. Okay. Cool. So let's look at another section, which is about representing a vector on a coordinate plane or the Cartesian axis. Okay. All right. So first of all, we can now given a coordinate system. Okay. So remember, for coordinate system is described by two axes, and then given this system, we can define two special vectors. Okay, two special vectors. Okay, namely the vector pointing in x direction and the vector pointing in y direction. Oh, sorry, not y. Okay, oops, sorry. So these two vectors, and then now to make things convenient, we'll see why it is convenient. Okay, it makes to make things convenient. Let's assume that these two vectors have a length which is equal to 1. Okay, and let me call these two this vector to be I, and this vector to be j. Now again, it is my habit to write it as I hat or j hat because they are special vectors. So I tend not to use the arrow sign. I will use the hat to denote them. Is that okay?
Yeah. Yeah.
Okay. So so here let me define the this notation to be the length of V. Okay. Then length of I is the same as the length of J, which is 1. Okay. Is it okay here?
Yeah.
All right. And in general, if a vector V has length 1, we call V a unit vector. Okay. That's just a definition. Okay. That's how we call these kind of vectors. Okay.
Yeah.
All right. Cool. And well, why do we introduce these two very special vectors, namely I and J? Well, because actually we can express any vector in terms in the following form. Okay. So the fact is, any vector, the 2D ones, okay, the 2D ones can be expressed as AI plus BJ, where A and B, sorry, not A and B are numbers. Okay. Okay. Can you understand this result first?
Yeah.
Okay. So now why can we do so? Okay. So I'm not going to tell you why generally. I will try to convince you using some example. Okay. So let's look at the following example. Okay. So let's try to sketch 5i plus 2j. Okay. So what does 5i plus 2j look like? Okay. So remember that the I and j, they are of length 1. So if we multiply it by 5, that means it is the unit vector. This is the vector pointing in the x direction and has the length 5. Okay. So that means it looks like this one. Okay. 5i. Okay. And then the 2j will be pointing up. Okay. Pointing up. So it's like this. 2j. Okay. Then the sum of these two vectors would be like this. So this vector is called 5i plus 2j. Okay.
Yeah.
Okay. So you can imagine why the fact above can hold, right? Because if you think about A and B are just trying to scale at this horizontal vector and the vertical vector here. And actually, if you have a vector, then you can just try to adjust this A and B such that it become, when you add these two vectors, you can get your desired vectors, right? You
Yeah.
understand what I'm saying?
Yeah.
So that's why this fact is true. Okay. Now this is not appropriate proof here, but then actually I just want to make sense of this. Okay. Okay. All right. Let's do one more example. Okay. Let's do one more example. Um, let's try to sketch negative I plus j. Okay. Negative I plus 3. Sorry. Negative 3I plus j. Sorry. Okay. So for this one you now, first of all, let's look at what negative 3i is. Remember, the negative of the vector is the vector that points in the opposite direction. And this time, we have a 3 here, which means the vector has a length 3. Okay, so that means it's negative 3i is pointing in this direction. Okay, and then plus j that means you point, it points upward. So it points upward like this. And then so the negative 3i plus j will be this this hypotenuse. Okay. Oh, sorry. This hypotenuse here, and it points like this. Okay. Is it okay? Yeah. Cool. So once you understand this, actually you'll see that it's very convenient to work with coordinates because of the following property. Okay. So property, the following property is, for example, you have AV plus AW adding together. Okay. Then you can just like real numbers, you can factor out the A. Okay. So that means this vector at the left hand side is exactly equal to A times B plus W. Okay. You understand this?
Yeah.
Okay. So once you have this, then for example, if you have P equals to 2I plus 3J and Q equals to 5I plus J, okay, then P plus Q is just like you add the numbers in I and add the numbers in J and then put them together, okay.
So it's
So
like complex numbers.
complex number.
Yeah, it's the
Oh
same
yeah,
number.
actually complex number is one example, right? Because actually complex, you can describe complex number using two, again, like these two unit vectors, namely the
Yeah.
1 and the I, right?
Yeah.
That's why all the complex number can be written as A plus BI, right?
Yeah. So it's like the same, right? And then you like
Actually, yeah, actually they are the same, uh, except that we can't really define multiplication vectors, okay? Or you can't define in a very uh, convenient way, because for complex number you can multiply I together, right? You can multiply real numbers, but then for vectors you so far we can't really like think of a proper way to define the multiplication of vectors. Okay, so anyway, back to this example. So the answer is 7i plus 4j. Is it okay?
yeah.
Okay, let's do one more. For example, p minus 2q. Okay, p minus 2q is also easy. Just 2i plus 3j minus 10i minus 2j. So you just script the I and j. So the first one is negative I, negative ai. The second one is negative plus j. Okay. So you see,
Yep.
it's very important. I mean, it's very convenient to work with this ij notation. Okay. All right. Next one. Um, the magnitude of vectors in magnitude of vectors. Okay. Now previously we did a really, I mean, now previously we need to draw this diagram before we can describe its direction and vectors, direction and magnitudes, right? And actually working with the ij notation, we can simplify this process in you can simplify this process. Okay, so so let's see why. Okay, so as I mentioned, any vector v can be written as ai plus bj. Okay, so for example, maybe let's not work with the general case. For example, 5i plus 4j. Okay, okay, so let's try to sketch it. Okay, let's try to sketch it. So when we sketch it, it's like 5i and 4j. So v is like this hypotenuse, right? Okay, and remember what magnitude means. Okay, magnitude basically means the length. Okay, so what's the length of this vector then?
Um, root 41.
Hmm? Sorry, I can't. Sorry, I can't hear you.
Square root 41.
Yes, square root 21, which is coming from Pythagoras, right? 5
Yeah,
squared. Oh, it's 21. Are you sure?
I said 41.
41. Yeah, 20. So 5 squared plus 4 squared. Okay, which is square root 41. Okay, so this is the magnitude. Okay, and you see in general, if this is A, this is B, then the length of V will exactly be A squared plus B squared square root. Okay, so that's how you work with the vectors under a Cartesian coordinate. Okay, so in general, V is AI plus BJ, then the length of V is just A squared plus B squared square root. Okay, so it's good to remember this. It's good to remember this because it's very inconvenient to work with this, and it makes I think it's easy to remember because it's just like the Pythagoras, right? Okay,
Yep.
all right. Let's try to do an example. Okay, so for example, uh, if P is 5 plus I, Q is sorry 5J plus I, or maybe 5I plus J. Sorry, 5I plus J, and then Q is 4I minus 2J. Okay, and then the question is asking you to find P plus Q, and then we take the magnitude. Okay, all right. So here you need to be so you need to be careful. Okay, so which part? Okay, so the thing that you need to be careful is about the uh you can't write this. Okay, the length of P plus Q is not equal to the length of P plus the length of Q. Okay, reasonable, right?
So you do the P plus Q first, and then you find the magnitude.
Exactly. So you need to be you need to find the addition. You need to find a sum, and then you get the magnitude. Okay. So P plus Q here is 9
80.
minus J. So that means the length of P plus Q is 9 squared plus 1 square root, which is 89 square root. Okay?
82.
As in 82, sorry. Yeah. 82. Okay. All right. So this is the magnitude, and also we would like to find the direction as well. Okay. So for direction, for example, the angle, find the angle between 4i plus 5j and the positive x-axis. Okay. So to find this, we need to draw the vector. Okay. So it's not that very difficult. You just, for example, this is 4i and 5j. Okay. So which means the vector looks like this. Okay. And then the angle between this vector and the positive x-axis is exactly this angle theta. Okay. And from from trigonometry, tangent theta is just 5/4. Okay. And then we take the arctan of both sides, and then we get theta is 51.3. And then we take, this is 3 SM. Okay. Is this okay?
Yeah.
Good. Okay. So okay, then so far we have found we have not go into physics, right? And now we can start talking about physics. Okay. So now so far we have just worked with a vector in case it is a displacement or it's just a abstract vector. Okay. And remember that apart from displacement or some abstract vectors, velocity can be described by a vector as well. Okay. So let's look at a case when the vector is a velocity. Okay. All right. So first of all, several facts. Okay. So first of all, we define speed to be let's define v to be the velocity vector first. Okay. If v is the velocity, then the speed is just the magnitude of velocity. Okay. This is just purely definition. Okay. And it makes sense, right? Because that's for example, it disregards the direction of the velocity. Okay. Okay. And also um, so for example, if your particle is going in this velocity, then the distance traveled in t seconds is equal to t times v, and then the length of v. Sorry, yeah, t times length of v. Is this okay?
Yeah.
Okay, so let's look at an example. Okay, so for example, v is 3i plus j meter per second. Okay, so a, find the speed, and b, find the distance traveled in 4 seconds. Okay, so let's look at A first. So for A, as I mentioned, speed is the magnitude of V. So speed is magnitude of V. And then remember the formula is just A squared plus B squared square root. So this is 3 squared plus 1 squared and then square roots, which is square root 10. Okay. Remember to write down the units here. Now the velocity, the unit is ms negative 1. So this is ms negative 1 as well. Okay. So this is A. B, find the distance traveled in 4 seconds. So you just multiply the speed by 4. So 4 square root 10 second meters. Okay. Is that okay?
Yeah, yeah.
All right, cool. Uh, okay. Next one. Also, what's convenient about this velocity vector is we can describe the position of a particle using a velocity vector. Okay. So the fact here is if, for example, your particle, let's draw a picture here. Okay. So for example, this is the initial position. Okay. This is the initial position. And then you're going on a direction with a velocity v. Okay. And then the fact is the position at time t. Let me just call this r. Okay, r. So the position at time t r, that's equal to r0 plus vt. Okay, can you understand this formula?
Uh,
You don't understand why, right?
no. Uh, what's what? No, no, no. I'm fine. I'm fine. Yeah, got it.
You understand why, or you
Yeah,
don't?
yeah, yeah, yeah. I get it. I get it. I get it.
You get it, right? Because like,
Yeah.
for example, let's test this formula for some t. For example, t equal to 0. When t equal to 0, the position is r0. Well, that's reasonable because that's the initial position, right? And then
Right.
for other times, it's going in this direction. So this thing here is just like the um that's the distance or the displacement at time t, right? This thing here is the displacement at time t. So somehow the displacement plus the initial position should give you the final position, right? Okay,
Yeah.
cool. So let's look at some examples. So for example, you have a vector. For example, the initial position. R0 is 3i plus 7j. And then v is 2i minus j. Okay. Uh, the task is to find r. Find r when t equal to 4. Okay. That's easy, right? Just plug all those things into the formula above. So R is, remember, R0 plus 4V. Okay. Then you just add the vectors just like what we did just now, right? So R0 is 3i plus 7j. And then 4v is 8i minus 4j, okay? Which is simply just 11i plus 3j, okay? So this is the position vector, okay? Now this is actually the position relative to the origin. So for example, if you take the magnitude of this vector, you just get the just get the distance of particle from the origin, but not the displacement. Now this you need to be careful because you need to understand what you're doing here. Okay, do you understand what I mentioned just now?
Yeah, yeah.
Cool. All right, and then let's look at another example, which is like this. Okay. Um, so for example, a particle is going in this direction. Particle goes in the direction sorry, let me restate the question here. So the question states that I think it's R0 is 2i minus 4j, okay? And then the particle is moving in constant velocity. And then 5 seconds, t equal to 5, then it is at the position r equal to 12i plus 16j, okay? And our task is to find the velocity, okay? V, okay? Again, this one we can plug in everything, just that the unknown this time is the velocity V, right? So this, remember R is equal to R0 plus this
Yeah.
time E equal to 5, so 5V.
2i plus 4j.
Yeah, so this one, the left hand side is 12i plus 16j, and the right hand side R0 is 2i minus 4j, okay? And this is 5V. Then we can solve for V immediately, right? So V is just 1/5 of 12i plus 16j minus 2i plus 4j. Then it is just 2i plus 4j. Okay, is it okay here?
Yep.
Yeah, cool. So so I think that's it for the chapter 2. Okay, so far we have we are able to work with vectors and then we can work with some problem involving velocity vector now. Okay, yeah. So any questions so far?
How much of chapter 3 have we covered?
Chapter 3, I think I've finished chapter 3. Okay.
Yeah.
Yeah. So next time we are going to cover chapter 4. Yeah, I think we'll be able to do so. Okay. All right. So any questions so far?
Nope.
No. Okay. So if there's no question, let's end the lesson here. Okay.
Okay.
Okay. So see you later. Okay. Bye.
Okay. Thank you. Bye.